So we are starting with the third unit and we are starting with the very first topic under the Statistical and Econometrical method series, and the topic is Simple Regression Analysis, its meaning and the assumptions. Here is the flow how we are going to cover the topic. So in Simple Regression Analysis, we study the interdependence or relationship between two quantifiable variables where a model is developed to study the relationship between these two. There is a relationship between these two where one would be the dependent variable and the another one will be the independent variable. So it works where we can identify the independent and dependent variable very first, and then we can collect the data on both variables. Then we use this data to fit a straight line that best describes the relationship between these two variables, and then we can use the line to predict the value of the dependent variable for given values of independent variable. There are several applications like in the field of finance, macroeconomics and several other fields where everywhere this is quite handy, and we can study the relationship between the dependent and the independent variables. So we know that it is used to model the relationship between the independent and dependent variable. The basic equation here used, as you can see here, it's y is equal to beta naught plus beta 1x plus e. It's just a form. Their beta naught can be replaced by a and beta 1 can be replaced by b and so on, where this capital Y is the dependent variable, the one we are trying to predict or understand. X in the equation is the independent variable which is used to predict the value of y. Beta naught will be the intercept. It is that point where the line crosses the y-axis, basically where the value of x is 0. Beta 1 is the slope, which tells how much of the value of changes for every unit change in the value of x, or we can say it's delta y upon delta x. E is the error term. It is that part which we could not explain in our model, so we take that all in E. So here is the linear regression graph through which the equation has been presented. Dependent variable y is y-axis, independent variable x is taken on x-axis. Beta naught from where the graph has been starting is the entire range where the value of x is 0, so it is intercept, and beta 1 is being taken as the slope. As you can see, it's showing the ratio of change in y with every unit change in x. So it's basically delta y upon delta x. As you can see here, there is 1 unit of x has been taken over the x-axis. So basically it's just to show that how it can be presented over the graph. These are basic 3 types of regression analysis: linear regression analysis, multiple linear regression analysis and logistic regression. So now we have taken an example to show how this entire thing works. Here year of experience, suppose there is a situation where we have taken certain data where years of experience is being denoted as capital X, where a series of 1, 2, 3, 4 in continuity has been taken, and salary has been taken which has been taken in thousands, is been denoted by Y, that is going to be shown on the y-axis, and where it's been taken as 40, 45 with a difference of 5 units. So now on this data we'll form our regression equation. So see, when we run the simple regression on this data, the equation that we have earlier seen, where y is equals to beta naught plus beta 1x plus e. So here y is the salary, which is a dependent variable, and x is the independent variable, which is the number of years of experience. Beta naught will be a constant, so we have taken here as 35. Beta 1 is 5. And x is of course there, which is the number of years of experience. So the basic equation becomes y equals to 5x plus 35, or we can put it like salary is equals to 35 plus 5 into experience, the number of years of experience. Now what this infers? So this explains the situation based on this model, that for every additional year of experience, the salary increases by 5,000. And if someone has no experience, like where the value of X becomes 0, they can expect a starting salary of 35,000, because here this entire term would become 0, so Y would be equal to 35,000. Since the value is taken in thousands, so it will become 35,000, as is shown here, you can see. Now we will see how this is plotted on the graph. So see here, the graph is in front of you on this slide. Here you can see, if we take the very first point, you can see the value of X is 1 and the value of Y is 40. Alright. Similarly, when we move ahead, the next point is where the value of X is 2 and the value of Y is 45. This is simply the workout of the equation where we are just simply putting the value of X, and simultaneously the value of Y is changing, that we can see further. So the regression line plotted along with the data points here. The red line here we already discussed. This is the line that represents the best fit linear regression model for predicting salary based on years of experience as a given condition here. So now, based on the equation y is equals to 5x plus 35, values taken in thousands, now we can put the value of x to see the change in the value of equation or the value of y. So let's start where we put the value of x equals to 1. So we'll put 1 in the place of x. The equation becomes y equals to 5 into 1 plus 35, which is equals to 40. So that is and so on further. So that is how it's been shown on the graph, as you can see, by those points on the line. So now comes the assumption part. Each and every assumption can comprise a chapter. So I guess more of tutorials would be needed to explain these in details. For now, we'll just get familiar with what they are. So the very first assumption is the assumption of linearity, that says that the relationship between the independent and the dependent variable should be linear, which means that the changes in the dependent variable are proportionate or proportional to changes in the independent variable. Meaning to say, if there is a 10% change in the independent variable, the dependent variable will also be changing in the same proportion, that is 10%. The second one is independence. So it says that the residuals, the errors, the term E, it should be independent, which means that the value of the error term for one observation should not be influenced by the value of the error term for another observation, or it will entire become a biased observation, which will lead to so much of error and incorrection. And then comes the next assumption, which is the assumption of homoscedasticity, which says that the variance of the residuals or the error term should be constant across all levels of the independent variable. If the spread of residual changes, it leads to heteroscedasticity. So the variance of the residual is not related to the independent variable. The next one says that there should be normality of residuals. That is, the residuals should be normally distributed. This is important for hypothesis testing and confidence intervals. We have already covered both of these topics in our earlier videos, but we can further cover it in another tutorial because this series is different. And then comes the another assumption, which says that there should be no multi-collinearity. Because in case of multiple independent variable, multi-collinearity, that is high correlation among independent variables, it shall be avoided. However, in simple linear regression with just one predictor, this does not apply. Then comes the assumption of no autocorrelation, that says that the residuals or the error terms should not be correlated with each other. This is particularly relevant for time series data, where errors in one period should not predict errors in another, or the whole test or the whole working out will go distort. Then the last one is the no omitted variable bias, which says that all relevant factors that influence the dependent variable should be included in the model to prevent the biased estimates. These assumptions holds a lot of value because variation of these assumptions can lead to issues like biased coefficients, unreliable standard errors, and incorrect statistical inferences. So we have to make sure that all these assumptions should meet when we go for SRA. So in the end, we can only say that simple regression analysis is really important, and it comes really handy when it comes to predicting the trends, or when we are trying to analyze relationship between variables, or in the process of forecasting, estimation of any kind of any simple decision making where we have certain dependent and certain independent variables. That is how it plays its very important role. Thank you.